Hi, my name is Matthew Abruzzo, and I'm a fourth-year astronomy PhD student at Columbia. In this video, I'll be highlighting two results from a paper that I wrote with Greg Bryan and Drummond Fielding and recently submitted to AppJ. First, I want to motivate this work. As you know, there's abundant observational evidence that stellar feedback-driven galaxy outflows are composed of co-moving multi-phase gas. The conventional picture holds that supernovae launch hot supersonic winds that accelerate and train ISM clouds via ram pressure. However, mixing between the clouds and wind complicates this picture. Idealized wind tunnel simulations indicate that mixing destroys clouds over a few cloud-crushing timescales. That's defined here. This is considerably shorter than the acceleration timescale. In this paper, we introduced a simple model for characterizing mixing using the system's phase evolution. So I'm going to show you a movie of a non-radiative wind tunnel simulation that conveys the basic idea behind our model. During the movie, pay close attention to the entropy phase evolution. For reference, gas from the cloud starts out down here, and gas from the wind starts out up here. So the main idea is that mixing increases the entropy of fluid elements originating in the cloud, and we can use this to characterize the cloud's destruction. So we're just going to focus on the blue histogram, the fluid elements originating from the cloud, and we can be more quantitative about this. This is showing the time evolution of that distribution, and from these measurements, we can characterize mixing by estimating k dot, which is the average rate at which mixing increases entropy. But it's often more convenient to consider k dot, which is the average time for a fluid element's entropy to double. So we find it very encouraging that k over k dot is within a factor of a few of the cloud crushing timescale. We also find that the model appears to roughly capture the cloud crushing timescale's dependence on density contrast and on the wind velocity, at least for supersonic winds. For subsonic winds, things seem to change. Additionally, our approach also reflects the slower mixing rate that you'd expect from having a strong magnetic field. So up to this point, none of the simulations have included cooling. But now we're going to switch gears, and we're going to talk about an interesting result related to turbulent radiative mixing layer entrainment. As you may recall from Drummond's keynote, this is the process in which mixed gas cools sufficiently fast that it facilitates the cloud's survival and entrainment. Gronke and O found that this process occurs when the ratio of the mixing layer's cooling time to the cloud crushing time is less than 1. The plot on the right illustrates the consequences of this process. The curves show the mass evolution of the cool phase from different simulations. The blue and black curves show simulations without cooling or with slow cooling, and these clouds are ultimately destroyed. But the cyan and magenta curves show simulations with fast cooling. These clouds not only survive, but show growth. The plot also illustrates that the ratio doesn't fully specify the cloud's evolution. The cyan and magenta curves have very similar values for the ratio, but the growth rates are clearly different. And it turns out that this difference in the growth rates arises because of differences in the cooling time at low temperatures. The faster growing case has a much smaller minimum cooling time. To prove this, we ran that this was indeed the root cause. We ran 4 identical simulations that only differed in their minimum cooling times. And we found that these simulations indeed reproduced the differences in the growth rates. And they also reproduced differences in the late time entropy distributions. So to summarize, the cooling times at the lower end of the cooling curve are important for determining the growth rate in turmoil entrainment. Thank you for watching.